Wheatstone's bridge. Wheatstone's bridge is an electrical circuit which is used to find unknown electrical resistance under balancing condition. Wheatstone's bridge. Wheatstone's bridge is used to find the unknown resistance in a given network. Now, let us see what is this Wheatstone's network. Here, the basic here is the principle. What is the principle of Wheatstone's bridge? In any circuit, if 2 points are maintaining same potential, in between 2 points which are maintaining same potential, current does not flow between the 2 points. Such 2 points which having same potential are said to be equipotential points. Always current flows from high potential to low potential. If the 2 points in an electric circuit maintaining same potential, we call those points as equipotential points. In between equipotential points, no current is passing. This is the principle of Wheatstone's bridge. Principle. What is principle? Current does not flow between equipotential points. Now, Wheatstone's network consisting of 4 resistors R1, R2, R3 and R4, which are connected to form a quadrilateral. R1, R2, R3, R4. Connected to form a quadrilateral. During this combination, 4 junctions are formed. A, B, C, D. Now, in between the junctions A and C, a source of EMF E is connected such that A and D is connected to cell's positive terminal. This is positive terminal. C is connected to cell's negative terminal through a plug key. Here A, C, B and D, all these 4 are junctions. In between junctions A and C, a cell of EMF is connected with the help of a plug key such that A is connected to positive terminal, junction C is connected to negative terminal. And in between the junctions B and D, a sensitive galvanometer is connected. This is the galvanometer. Due to the source of EMF E, current starts flowing through all the resistors and in all the branches of this circuit, such that from cell's positive terminal, I currents comes up to the point A. At junction A, I splits as I1 and I3. At junction A, I splits into 2 parts, that is through R1 resistor I1 current, through R3 resistor I2 current. At junction B, some part of this I1 flows into galvanometer as Ig. Galvanometer current is Ig. And remaining current, that is I1 minus Ig, passing through R2. This one. And at junction D, I2, Ig, both combined as I2 plus Ig will flow through this R4 resistor, I2 plus Ig. Here, at all junctions, we are able to apply Kirchhoff's current law. So at junction A, incoming current is I split into I1 plus I2. That means I is equal to I1 plus I2. At junction B, I1 split as Ig and I1 minus Ig. At D, I2 entering, Ig entering. These two combined as I2 plus Ig, leaving the junction D. And at junction C, I1 minus Ig, which is flowing through R2, and I2 plus Ig, which is flowing through R4. These two combined at C. Again, as I, it flows. At junction C, current I1 minus Ig and current I2 plus Ig meet and flow together as I. Observe here. This one. I is sum of I1 minus Ig and I2 plus Ig. Plus Ig minus Ig cancel. I1 plus I2. I1 plus I2 is nothing but I. This is the circuit. What is the principle of this Wheatstone's bridge? If 2 points maintaining same potential, we call them as equipotential points. B point and D point, call them as junctions. Junction B, junction D. These two are the 2 points. If these two junctions B and D maintains same potential, means if VB is equal to VD, then current does not flow through BD branch. Current does not flow through the BD branch if B junction potential, D junction potential both are same. Means VB is equal to VD. Current through this galvanometer is 0. Hence, Ig equal to 0. No current flows through the galvanometer. Current will not flow in branch BD of the network if and only if VB equal to VD. B point potential, D point potential. If these two potentials are same, no current flows through BD branch. That means the BD branch current is Ig, galvanometer current, that is 0. If VB equal to VD, then Ig equal to 0. Galvanometer current is 0. This happens to be true only if R1 by R2 is equal to R3 by R4. This is the balancing condition of Wheatstone's bridge. This is known as balancing condition of Wheatstone's network. Now, proof of that R1 by R2 is equal to R3 by R4. For that, apply KVL, Kirchhoff's voltage law, to loop A, B, D, A. For ABDA closed loop, we are going to apply KVL, Kirchhoff's voltage law. What is that? I am moving from A to B. If the current is along the same direction, then the product of current and resistance, that is negative. Minus, I am moving from A to B. Current is also flowing from A to B. So, along the direction of motion in the circuit, the current is there. The product of that current and resistance is negative. So, current enters from here, leaves from here through this R1. So, this is positive potential, this is negative potential. The potential difference here is I1 R1, that is negative, minus I1 R1. Next, I am going to move from B to D in the circuit. B to D. So, the galvanometer current is 0 under balancing condition plus this part becomes 0. G is the resistance, Ig equal to 0, Ig into G, 0 into capital G becomes 0. So again I am going to move from D to A in the circuit. D to A. While I am moving from D to A, current flows from A to D opposite to my motion in the circuit. So those product of current and resistance is considered as positive. Means current in this AD branch is I2, resistance is R3. I2 R3, this product is positive. Why? Because current flowing opposite to the flow direction in the circuit. So here in this closed circuit ABDA, there is no cell. So in this closed circuit, there is no cell means sum of minus I1 R1 plus I2 R3 which is equal to 0. Now from here I1 R1 equal to I2 R3. This is for ABDA closed loop we apply KVL, Kirchhoff's voltage law. Take this equation as equation number 1. I1 R1 equal to I2 R3. Now I am going to apply this KVL to another loop BC DB. It is a closed loop. For this loop I am going to apply KVL BC DB. I am moving from B to C. Current flow is also along the BC direction. Hence the product of I1 R2 is negative minus I1 R2. Next from C to D. In the circuit I am moving from C to D. Current is from D to C in this branch DC. So that means current flowing opposite to the my motion in the circuit. Means the product of I2 R4 is taken as positive plus I2 R4 up to D point. Now D to B I am moving. While moving from D to B, current in this galvanometer is 0. Current becomes 0. The potential difference across DB points is 0. So the loop was closed. Hence the algebraic sum of product of current and resistance in various branches is equal to 0. Why? Because 0 here in the closed loop BC DB also no source, no EMF source, means there is no cell in BC DB part. From here I1 R2 is equal to I2 R4. Take it as equation number 2. Now from 1 and 2, I1 R1 equal to I2 R3. First equation. I1 R2 is equal to I2 R4. Second equation. Taking 1 by 2. Therefore, by take 1 by 2, we get I1 cancel, I2 cancel. R1 by R2 equal to R3 by R4. This R1 by R2 is equal to R3 by R4 is the formula for Wheatstone's bridge under balancing condition. R1 by R2 is equal to R3 by R4. This balancing condition of Wheatstone's bridge can be obtained by using Ohm's law. Why? Because we are taking potential difference between any two points as product of current and resistance, V equal to IR, as well as one more point, that is potential at A, potential at B, potential at C, potential at D are taken as VA, VB, VC and VD are the potentials at points A, B, C, D. This is the circuit of the Wheatstone's bridge. If no current flows through this BD branch, meaning is what? VB equal to VD. Potential at B point is VB, which is equal to VD under balancing condition. Means through this galvanometer, current is 0. Which implies minus VB equal to minus VD. Now, I'll do VA on both sides. Add VA on both sides of this equation. VA minus VB is equal to VA minus VD. What is VA minus VB? VA minus VB is the potential difference across the ends of resistor R1 which carries I1 current. So we apply Ohm's law. VA minus VB equal to potential difference. Nothing but IR. What is I? I1. R is what? R1. So hence VA minus VB is equal to I1 R1. Similarly, VA minus VD. Potential difference between junctions A and D. VA minus VD. Which is equal to current in this branch, that is I2, into resistance in that branch R3. I2 R3. Which implies, therefore, I1 R1, that is the potential difference across A and B, is equal to I2 R3, that is the potential difference across A and D. That is considered as equation number 1. Similarly, VB equal to VD. Now minus VB equal to, I am going to do VB minus VC is equal to, here VD minus VC. On both sides I subtract VC from VB and VD. So VB minus VC equal to VD minus VC. What is VB minus VC? Potential difference across B and C junctions. What is the amount of current in this branch? I1. What is resistance? R2. Means I1 R2 is the potential difference between B and C points. Similarly, potential difference between D and C point is I2 R4. Means I1 R2 is equal to I2 R4. Take it as equation number 2 from 1 and 2. First equation is I1 R1 equal to I2 R3. First equation. Second equation is I1 R2 equal to I2 R4. Second equation. Do 1 by 2 again. I1 cancel. I2 cancel. Then we get R1 by R2 is equal to R3 by R4. This is the Wheatstone's bridge. What is the condition for balancing Wheatstone's bridge? That is R1 by R2 is equal to R3 by R4. Now MCQs. Question is, Wheatstone's bridge can be used to find, to compare two unknown resistors, to measure the small strain produced in the hard metals, as the working principle of meter bridge. All the above. Correct option is all the above. It is used to find the unknown resistance, used to compare the two unknown resistors, to measure the small strains produced in the hard metals, and the Wheatstone's bridge is the working principle of meter bridge. All the given options are correct. Second question. Wheatstone's bridge is most sensitive when the arms ratio is options equal to 1, less than 1, more than 1, 0. If the arms ratio value is equal to 1, means whatever the 4 resistors we used, R1, R2, R3, R4, all the 4 resistors are identical, then only R1 by R2 is equal to R3 by R4. So the arms ratio must be equal to 1. Now, one problem based on Wheatstone's bridge model. The effective resistance between AB in the given circuit is. This is the circuit. In between AB points, we are going to find the equivalent resistance. Here, this is the model, looks like Wheatstone's bridge. Now, the options given are 10 ohm, 10 by 3 ohm, 20 by 3 ohm, 40 by 3 ohm. How to do this problem? Let us consider this 2 ohm as R1, 3 ohm as R2, 4 ohm R3 and 6 ohm as R4. Under balancing condition, what is balancing condition of Wheatstone's bridge? R1 by R2 is equal to R3 by R4, which implies what is R1? 2 ohm. What is R2? 3 ohm. 2 by 3 is equal to R3 by R4, 4 by 6. The 4 by 6 value is also 2 by 3. Means here R1 by R2 is equal to R3 by R4, satisfying in this circuit. Means it is the Wheatstone's bridge model under balancing condition. Means Wheatstone's bridge under balancing condition, there is no current between these 2 points. Between these 2 points, let us say X, Y. In between X, Y, no current is passing. Why? Because Vx equal to Vy. Means the current through 5 ohms is 0. Current in 5 ohms equal to 0. Then how this circuit changes? Here this is 2 ohm and this one is 3 ohm. Similarly, here onwards 4 ohm. Here one more is there, that is 6 ohm. This is the B point and this point is A. Here I am neglecting 5 ohm. Why? Because there is no current through this 5 ohm under balancing condition. Under this balancing condition, current through 5 ohm is 0. Now, it becomes easy to find the equivalent resistance between A and B. How? Here 2 ohm and this 3 ohm. These two are in series. Equivalent resistance here is 2 plus 3, that is 5 ohm. What is this? 2 plus 3, 5 ohm. Series combination R1 plus R2 is the formula. Similarly, 4 ohm and 6 ohm. These two also in series. The equivalent resistance here is 10 ohm. How 10 ohm? Because R1, R2. Here also these two are in series. Equivalent resistance is nothing but sum. 4 plus 6. Now how the circuit changes? Above, this is A point. Above here, in place of 2 and 3, I am using a single resistor 5 ohm. And here below 10 ohm. These two connected together at here, two ends of the 5 ohm resistor and 10 ohm resistor. This point is B. Now, this 5 ohm and 10 ohm, these two are in parallel. 5 ohm and 10 ohm are parallel. What is formula for equivalent resistance in parallel combination? R1 R2 by R1 plus R2. That means resistance across AB is equal to R1 R2 5 into 10 by R1 plus R2 5 plus 10, that is 15. Here 5 ones, 5 threes. So what is the answer now? Resistance across AB part is 10 by 3 ohm. This is the answer. Now solution. 2 by 4 equal to 3 by 6 means bridge is under balancing. Then the equivalent resistance is 2 into 4 by 2 plus 4 plus 3 into 6 by 3 plus 6. This is another model he used. The answer here is 10 by 3. For us also, it is 10 by 3 ohm. So second option is correct. Next question. Effective resistance between A and B in the given circuit. All the resistors are R like that. The effective resistance between AB points, in between these 2 points, what is effective resistance? The options are 6R, R, 2R, R by 2. Solution. Here, the effective resistance between A and B is R into R by R plus R, Wheatstone's bridge model only, plus R into R by R plus R. That means R by 2 plus R by 2, which is equal to R. So, this is similar to Wheatstone's bridge. So, the effective resistance is R itself, R plus R, which is equal to R by 2, capital R equal to R by 2. So, option 4 is correct.